Public key certificates, or digital certificates, build on public key authority but adapts it so that the keys can get distributed without contacting a public key authority in real time, which helps with the scalability issue. In fact, public key certificates are used for the internet, which is comprised of many computers. A certificate binds an identity to public key, with all contents signed by a trusted public key or certificate authority, or CA. Like the previous public key authority, the certificates are signed by the CA, so the users who are aware of the CA's public key can verify the signatures. However, because certificates can be distributed before the actual communications for data transfer, the certificates also contain the validity time information. There are design requirements for public key certificates. First, any user can access and read a certificate. And second, any user can verify the certificate. Third, only the CA can create or update certificates. And fourth, the currency and the validity of the certificate should be clear to any user accessing the certificate. To accomplish these requirements, the CA's certificate authorities use digital signatures to sign the certificates, which require the distribution of the CA's public key to the users. Also, a universal standard is needed so that anybody can read the certificates. One standard has become widely accepted for formatting public key certificates, the X509 standard by the International Telecommunications Union, or ITU. X509 certificates are used in most networking security applications, including Secure Sockets Layer, or SSL, Transport Layer Security, TLS, which are the basis for HTTPS, IP security, secure electronic transactions, and securing emails. Next to me is an example showing the digital certificate used for Transport Layer Security, or TLS, when browsing the web. It shows the user, uccs.edu, the CA identity, those CA, and the validity information. So let's review the protocol with the users Alice and Bob and the CA. Alice wants to communicate with another party, in this case Bob. Alice sends her public key to the CA, the certificate authority. The CA responds to Alice by sending her certificate C-sub-A associated with the user Alice. The certificate contains the identity, the corresponding public key, the time validity information, and is digitally signed by the CA so that anybody receiving the certificate has assurance that it came from that CA. Alice can now take this certificate C-sub-A and share it with anybody whom she wants to communicate with. For example, Bob in this case. Similarly, Bob can also ask for his certificate C-sub-B to securely share his public key with other users, and then use the certificate to distribute its public key. To manage such public key certificates, public key infrastructure, or PKI, is the system infrastructure which involves hardware, software, policies, and procedures that are needed to create, manage, store, distribute, and revoke digital certificates based on asymmetric cryptography. The PKI is designed to enable secure, convenient, and efficient acquisition of public keys. Internet Engineering Task Force, or IETF, developed such certificate-based architecture based on X509 certificates. The PKI also adds functionalities and the corresponding responsible entities for registration and revocations. For example, by using dissemination of a certificate revocation list, or CRL. Such revocation mechanisms provide ways to update certificates in the case of a certificate compromise. Such PKI and public key certificate provide a centralized mechanism to distribute public keys, which in turn can be used for sharing symmetric keys. And these are used to anchor the security of the networking even in large networks, such as the internet.